Great. So Oliver will introduce us to the HELIO model of open science and outline why research software engineering is now more important than ever before. Oliver is a research software engineering working on solutions for managing, publishing, and archiving research data and research software. His mission is to bring these two worlds together to promote open science and reproducibility. Based at the Central Library of the Forschungszentrum Jülich, he is, amongst other activities, co-PI of the Helmholtz project, which aims to develop a new key infrastructure element for automated metadata-rich research software publications. So welcome, and we are looking forward to your talk.
Yeah, thanks for having me and for a warm introduction. As Antonia already said, I'm Oliver Bertuch. I'm working at the Forschungszentrum Jülich. Within that team, Open Science, I'm not alone working on solutions and ideas. Unfortunately, my colleague Monica Gonzalez Marquez, which did actually most of the work that I'm presenting today, was ill, so she cannot be here today. I hopefully will be a good proxy for her. All right, let's get this started. Maybe I should activate the timer so I don't talk too much. Here we go. First of all, I would like to get us on the same page. We heard a lot about terms like reproducibility and replicability and all these things out there, and there are like a bunch of definitions for this. And for this talk, I would like to go with the definition that has been developed by the Turing Way community, which is pretty much generalizable to what all of you probably are doing. And first of all, reproducibility means, in their definition, that if you use the same data and apply the same analysis, hopefully over and over again, you will find the same answers. And replicability is in contrast to that you have different data, the same analysis, and you will find qualitatively the same answer again. So it's not the same answer as before in reproducibility, but there's a tiny nuance here. Use different data, but still go to a qualitatively same answer. A robust analysis would be something that is applied to the same data, but with different analysis, for example, some other kind of tool, or maybe with a different version of the dependency, and you would still be able to find the same answer or qualitatively similar answer. And the generalizable answer, that's like the goal for a lot of people here that developed some kind of tool or some new scientific method, is about applying different analysis to different data and still find the same kind of answer. Obviously not the same answer, then it's, well, but there seems to be something in it, a principle, a new thing that you can discover that is generalizable. That's why it's called generalizable. So for a second, let's imagine that we would be doing something that is quite common these days. We're looking for a new scientific method to answer some kind of research question, and we do this by having the help of a trained AI model, and we come up with that. That's great. It's a great tool. So, but after having that work done, we should ask ourselves some questions, like how can we actually be sure that this model that we just trained can be trusted? What happens if we train the same model again with the same data? Are we sure this is still the same neurological network? Does it give the same answers? What happens if we apply the model to new data, like replicability? And what happens if we at some point discover, oh, we did have some kind of selection bias within our training data set? What if we never discover that kind of thing? So how can we be sure that we don't fall into that pitfall? And last but not, or the next point would be that at some point we hopefully share this model, because obviously we're doing great research, we want to talk about that. And now we send there, and no one is actually able to verify that model because we just shared the model. But maybe we didn't share the training data, and maybe we didn't share the code. Or, well, we couldn't maybe, because it's not hard sometimes. And if we did all the steps, and we tried to do the best of our knowledge, maybe if it's still not reproducible or more, like generalizable? So the problem that we're facing is that we're kind of stuck in a linear universe. The current situation in science is very often that we have one sun, one universe, and it evolves all around scientific articles. And usually scientific articles cover the literature, cover algorithms and methods. Algorithms, for example, if you're looking into computation papers, you will find a lot of those. It will also cover analysis. And if you use some kind of AI thing, you probably are talking about that as well. Maybe outline how you like place the layers and how your general approach is working, but probably not too many details, because that's a lot of details and there isn't enough space in a paper. So things become really brittle once you try to look outside of that. There is like an astroboid built around this kind of thing. So if you're looking for the code that one has been using, very often you end up with like, yeah, we just dumped it on GitHub, or yeah, it's available upon request, or whatever. And the data is also very often not shared, or it's hard to get there. And there's a lot more detail that has been involved while doing your research. And here it's not on the map at all. It's not covered by an article. So there'll be dragons beyond that point. Let's also fill this with a more real-life example. Once upon a time in 2020, there was a group of researchers at Harvard that said, hey, we have a great research done. It's about, we trained a model, a neurological network, to discover cancer, more specifically breast cancer, in images. That's great, right? So if we can detect cancer better, isn't that something we all should have? Like, this is helping people. But soon after that, another group of people reached out and said, did a reply to this article, a group around Heibe Kainz, also in 2020, and said, hey, well, this is nice, but it's not reproducible. And this is a problem because, well, obviously we're trying to apply that kind of analysis to images, and we want to help people, but how can we actually be sure that this works? And that's surely no problem at all when we're talking about cancer, right? So like some kind of male detection, false positives. What about false negatives? And the reply to this reply again was, yeah, well, we did share the model and we had some code, and yeah, we used PyTorch. And well, the other stuff, like the scripts that control how we actually set up the whole pipeline to train the thing, that didn't seem to be of interest to other people, so we didn't share that part. And also the data set, yeah, well, we're very sorry, but this is classified. You have to apply to some kind of, in the UK, to NIH thing to get access to these images. We're very sorry, we did the best, but that's where we are. Sorry. I mean, I can understand that position, I can relate, but this is a problem, right? It's still not replicable. You cannot verify that this is actually working the way that we are looking at things right now. They did have this great Nature article, but that's kind of it. And why are we there? So things to learn here would be like, how about we create and reference data and code publications, like fair code publications. And fair doesn't mean you have to open everything, but at least make it findable, make it accessible, even by just providing the metadata. Hey, something is here and I've used it. If you want to take a look at this, come talk to me, but at least you can make sure that people understand what kind of things you're using to express dependencies. Also, what about if we had more documentation about this whole thing that we could even share, like every step of the way we would write down and try to share this in a shareable provenance way? What if we would deduct the text publication at the end of our research from this kind of documentation and also give references back into this documentation, like, okay, so from this part of the documentation, I know this kind of conclusion. And wouldn't this even enable us to do a kind of a peer review before it is even published within a team of people. Like, we use the documentation to make sure that this stuff is reproducible. And wouldn't it be even better if all of this would give us some more credit and even money for going this kind of extra mile? Let's talk about how we could reshape things a little. This is the heliocentric model of scientific labor. And the idea is that we need more coverage of all the things out there that are currently happening. And we're transitioning from having the sun as a scientific article to having in the middle and in the focus of all of our things we're doing, the scientific process itself. So something that you're probably doing all day long, doing some kind of science. And the satellites you're seeing here, the analysis, the question background, the narrative, the results, and discussion are like the key points, because under these things, you can collect subtasks. I've outlined a few subtasks here that are kind of targeted towards computation in science. So probably in your research, not all of these tasks might be applicable. You might have different things in addition. You might find some of these tasks in different satellites, so they appear in multiple places, but still it shows pretty clear that there's more than just, yeah, here's the algorithm, here's like the result, and maybe some discussion of the method. It really takes a lot more. The sharing of all of this also means that if you want to go from one place to another, for example, if you want to talk about analysis and narrative and how these two things connect, you will need documentation all over the place. So going places in space means you will need to have a map that unveils like where are things, how large are they, how do I get there, how can I actually land on a planet, what kind of things can I expect. And having these coordinates on that map means you will need references in some way, either as publications or at least have some kind of persistent identifier for all these things. And obviously, if we want to travel somewhere, we will need labor. This will require work. So the importance that we already saw here, like a lot of technical stuff that looked like software engineering appeared here, is also unveiling why research software engineering is of utter importance for the scientific process and the science that we do every day. The key aspect that is hidden in all of these satellites and all of the subtasks of the satellites is that at some point, the code you're writing will be in control. It is kind of a gatekeeper. It will control the narrative. It will be either an executable analysis. So that means that your code is of crucial importance to actually do the science you're doing. It might be in control over the execution of some analysis. For example, you might want to control with some written code a microscope. Or as we saw earlier with Deborah, you're in control of how your analysis is conducted. And also, code might create unexplainable analysis. For example, if you use some kind of neural network, the matter of explainable AI is still under research. It's not easy. It's a kind of a black box, and you need to be you need to use different methods to actually be sure that it's doing what you want it to do. And all of this doesn't come for free. It obviously needs people that know things. So quis custodiet ipsos custodiet. Who is watching the watchman? We need to find strategies how to deal with this kind of hazards that are there, that code might actually break our neck when we find that we made some kind of error in the code. The strategies we can apply here is, first of all, that open sourcing of research as a default. So make it open if it's possible. Just change your mind to not hide away things, but instead just make it open will help already. by a great deal because people can actually help you in ironing out any kind of faults or other stuff that you might have in your code. Obviously, developing the code and better code will kind of need help from people that know what they're doing. A lot of science are not trained software professionals, so it will require funding to either hire these people or to train scientists to be like them and to be better coders. And we will need to have some kind of support and credit system for these people, especially for scientists that are not software engineering specialists, and also for the research software engineers that we might hire at some point. And there's things on the way, at least. We have DORA, the San Francisco Declaration of Open Research Assessment, and COARA, which is a EU-based thing that is joined by organizations and individuals that are saying, okay, we want to do things differently. We don't want just to look at text publications, and instead, we want to look also at software and data and all the other things that are out there. And this leads to that catchy phrase of better software, better research, which you might have come across already, coined by the SSI, Carol Goebel, and is really about if we do better software, we will have better research in the end. So all the things that I've been talking about don't really require you to make things open, but probably it's a good idea to make it open. So at some point, you might have the need that someone should be looking at your stuff. And if you want your stuff to be reproducible by others, it makes their job a lot easier if your things are open. So open science or just science is a kind of labor. So you will need to document things accordingly. And the open in science comes from sharing this documentation and obviously also the results. And sharing as much as feasible. Of course, it's not always possible to share everything, but we should try. Because sharing is caring, and maybe some of your research might actually be inspiring other people. We just heard in the talk from Deborah that a lot of people in this room popped up and said, hey, I have a similar problem. So this is where this thing starts. If we make things open, we can find new possibilities that were not there before. So your research and your methods, your results might make it from one star system, one scientific process, yours, to someone else's. And probably that's a good thing. What does all of this mean in practice? So, as I said before, we need to adapt as necessary. There's different scientific domains and different sizes of research, different sizes of the different tasks that we're looking at. We have different gravity, therefore. So that means you need to pick what works for you and make it open if possible. You shouldn't be alone because science obviously needs diverse experts. All of the stuff that we have seen before, like show me one scientist that actually would be a professional software architect. If you need in your research some kind of software architect, that's probably very hard to find. You probably need to train professionals for that. So we cannot just offload all of this on scientists and say, yeah, well, you'll do that. It'll be fine. We need to allocate some funding for RSEs, for research software engineers. And these people, and also obviously the scientists, need incentives to continue working on this. So we need credit for all of these types of works. And it's totally skewed towards text publications now. And one of the things you can do in practice is start as scientists to create data and software publications. Because if this thing becomes traction, the chance is there that we actually can transform the system. Obviously, not being alone also means it's always easier to do things as a team. Challenge a friend to be reproducible. like share your research with a friend and say, let's do a repro hack. I've linked here the repro hack thing. You can click on that in the slides later if you want to. That is about hosting events where people team up in pairs of 2 or more or whatever and say, hey, here's a paper, here's my paper, here's your paper. Let's try to reproduce with the materials you provide, and let's see if we can actually make it reproducible or if it is already reproducible. There's tools, like we're conducting research on problem arcs. There's Git, we've talked about that already, we heard about from Deborah. There's DataLab, we've also heard about that, and there will be a workshop. And electronic lab notebooks and stuff like protocols.io, which is about creating and tracking provenance. That's like the documentation we need. We need to have the proof that the science we conducted actually makes any sense. And last but not least, training and support is key. So open science and reproducibility is not just a bunch of tools. It's a mindset and it's a challenge. So we should address this together. And this is happening. So if you want to learn more about reproducibility and all the aspects that come with it, take a look at the Turing Way guide. Again, all of these are links. You can just click on the icons. This is a very large collection of a lot of knowledge done by the Alan Turing Institute in the UK, and it's really great and gives you a lot of details about a lot of aspects. We have within Helmholtz, and also accessible to others, so this is not limited to Helmholtz, the HELIO, the Helmholtz Research Software Engineering Platform, which is doing very regular seminar series and hackathons and workshops to conduct some kind of, or to apply some kind of thing to your research. For example, they recently hosted a continuous benchmarking workshop. We have the experts from the German Reproducibility Network, which are here to help you people. Just reach out to them if you're interested to join an organization about reproducibility. And last but not least, we have the Helmholtz HiFIS software services, which is a help desk to help you when you run into problems while developing some kind of software. And they also do a lot of training with the different topics around software engineering. That's it. Thank you. I should mention again, a lot of the HELIO stuff has not been done by me. Most of it actually has been done by Monica Gonzalez Marquez. So if you have any questions about HELIO, please make sure to contact her because she's the right person to address about HELIO. And there's links again. You can find her online, the profile of the research center. And I'm more geared towards like software publications and research software engineering, research data management. Thank you.